Hey guys, this is Miss Kato speaking to you from her home because I am faced with some technical difficulties and there's a lot of work to do. So over here I'm going to be talking about these subtopics, and we'll be covering chapter 13.1 and 13.2 of this first podcast of Unit 2. We have talked about the particular drawings of gases and how different they are from liquids and solids. Being that gas particles are much more spaced apart, they are easy to be compressed. We talked about the kinetic theory of gases. These notes should already be in your notes. However, if you have not gotten them in your notes yet, then please stop this video or pause this video and record them into your science journals. In order to elaborate on this characteristic a little bit further, I'm going to show you guys the websites that I have showed you in class. So we have gas particles moving in a container right now. These blue dots represent the gas particles, and we see that if you take a look at the gas particles, you see that some of them are moving much faster than others. So even in one sample of gas at a certain one temperature, you see some gas particles are moving faster than others. The gas particles themselves are represented as small, hard, spherical particles, and the particles are so small that their volume is considered to be insignificant in comparison to the relative size of the container. There's no interaction between the particles, no attraction or repulsion. They are moving independently of each other, and they are constantly moving, rapidly moving in straight line path until they collide into something or each other. And the collisions between these gas particles are said to be elastic, 100% elastic, meaning that the total speed of the particles before the collision is the same as the total speed after the collisions. So as I have left this simulation going for about a minute, you see that the total speed has not changed at the beginning of the minute in comparison to the end of the minute. So let's talk about the gas particles diffusing. So here is my red dot, and we're just going to follow the red gas particle in this simulation. So remember that the gas particles are supposed to be moving very, very fast. So imagine that they are moving very fast. The total distance that the red gas particle travels is represented in this blue line. However, its distance from its original position, its original location, is represented in the red line. So as you can see, the red gas particle is moving back and forth and side to side, but it's not able to move very far from its original location because it is colliding into so many other gas particles in between. This simulation shows you the random walk of the gas particle. As it diffuses, it's moving very, very fast, but it's not able to move very, very far, and that is shown on the graph on the right. As you can see, it's following the path of the red gas particle, and as it moves, it's moving back and forth and side to side, but it doesn't really move very far from its original location. So in the many vocabulary word that I have put into your Unit 2 objective sheet, I told you to describe many vocabulary in terms of kinetic theory. So what do I mean when I say kinetic theory? I'm talking about, if I can find, I'm talking about describe pressure in terms of moving particles. So now, gas particle is the amount of force applied onto a given area by particles. So when I say force, I'm talking about how often and how hard the particles hit a given area. And so pressure could also be thought of as force per area, and that force is defined by how often and how hard the particles hit that area. So the topic of pressure leads us to explain air pressure, also called atmospheric pressure. Atmospheric pressure is caused by the weight of the gas of the atmosphere striking surfaces of things from every direction. Atmospheric pressure was first measured with a tool called a barometer. So an Italian physicist / mathematician in the 1644, around 1644, created this tool to measure atmospheric pressure, and what he did was he got a long tube of glass and filled it with mercury. And so it's filled to the brim with mercury, and had a dish of a pool of mercury. Also, he flipped this mercury tube onto the pool of mercury, and he saw this. He saw that some of the mercury was heavy enough to be pushed out of the tube into the pool, leaving this space right here with pretty much no particles. So as he flipped it, no air particles were able to get in. And so in this little section of the barometer is what we call a vacuum, and many of you guys have used this word, and it just means space without particles. I know a lot of people have been using this term vacuum a lot, especially with the CANCO project, but vacuum actually means space without particles, and I think a lot of people have been using this word as equal to low pressure, but low pressure does not equal to a volume, but actually vacuum equals to no pressure. So please be careful how you use this word vacuum. So there is no particles in here that is hitting onto the surface of the area, the surface of the mercury. However, there are air particles out here that are hitting onto the surface of the mercury here. And so the question was why, how, or what was keeping this level of mercury up in the tube, and the explanation was that the particles of the air was pushing down the pool of mercury here and pushing up the mercury inside the tube. At sea level, is the standard pressure, and at standard pressure the height of this mercury is 760 millimeters of Hg, or mercury, which is the same thing as 76 centimeters of mercury. Standard pressure was originally measured in millimeters of Hg according to the barometer that was made by Torricelli, and so we call the units of pressure in millimeters of Hg as 760 torr also. Okay, So standard pressure is 760 millimeters of Hg and 760 torr, and also 1 atm, which is a unit that Americans go by. Most of the countries around the world use, however, the 101.3 kPa. We also talked about this pressure represented in many units also being represented as 14.7 pounds per square inch. So these are all equivalents of each other, and we can use these in conversion factors to convert between units of pressure. So let's give you an example. At Clouds Rest, it is a 15-mile day hike in Yosemite, 10,000 feet above sea level. It has an atmospheric pressure of 523. What is the atmospheric pressure at Clouds Rest in kilopascal and in torr, and also in atm? So if I were to take the 523 millimeters of Hg and I were to convert it into kilopascal, I would put this over 1 and I would use the millimeters of Hg unit as well as the kPa unit and put these into a conversion factor. In my conversion factor, I'm going to put the millimeters of Hg down here, 760, and I'm going to put the kilopascal up here, 101.3 kPa, and that should give you the kilopascal. And now you know how to convert between the units of pressure. I want to talk about temperature a little bit. So temperature can be represented in either Kelvin, Celsius, and Fahrenheit. So these formulas are provided in your cruncher. So you do not have to memorize this, you just need to know where it is in your chemistry cruncher. Kelvin scale temperature is equal to the Celsius plus 273.6, but I'd be happy if you just uses 273 just for simplicity's sake. Fahrenheit and Celsius, please know these formulas, or please know where they are in your chemistry cruncher. Temperature can be defined as, or can be defined in terms of kinetic energy or kinetic theory as the average speed of the molecules. So I'm not talking about total speed, I'm not talking about the individual particle speed, but I'm talking about the average speed of the molecules. So if the average speed of the molecules generally is increased, then the temperature is higher. If the average speed of the molecule slows down, then it is cooler. Kelvin units are convenient when we do gas conversions because they are directly proportional to the average kinetic energy of the particles. So let's take for instance this question down here. By what factor does the average kinetic energy of the molecules of a gas in an aerosol can increase when the temperature is raised from 27 degrees Celsius to 627 degrees Celsius? So if I were to now convert the Celsius temperature into Kelvin, I would add 273 to this and I would get 300 Kelvin. Likewise, with the 627 degree Kelvin, I add the 273 to it, and now I am at 900 Kelvin. And as you can see, the temperature increased by 3 times. So my kinetic energy also must have increased 3 times. Okay? So if I were to actually talk about this in terms of kinetic theory, if the temperature goes up, I said that the kinetic energy is high. So here's my high temperature at high kinetic energy. Here's a little bit lower temperature at a low kinetic energy. At a lower temperature, the kinetic energy, or the average speed of the particles, is lower. And at a very, very low temperature, the Kelvin energy, or Kelvin scale, or the energy, kinetic energy of the particles must be 0, and this point is at 0 Kelvin. At 0 Kelvin temperature, the kinetic energy of the particles is 0. So the kinetic